Well, ladies and gentlemen, this is my schematic how to decode DCF77 radio transmitter time signals. Maybe you don't know, but the DCF77 transmitter, the DCF77 transmitter is in Germany, has a range of about 2000 kilometers, and it transmits on the long wave at a 77.5 kilohertz. Each second it sends a 0 bit or a 1 bit, and it does it by each second. This is 1 second, and it sends a 0 bit or it sends a 1 bit each time. A 0 bit means the strength of the transmission is reduced by 15% for 100 millisecond time each second. If it decreases its transmission strength 200 milliseconds with 50%, it means a 1 bit. The rest of the time it transmits at full power. There is something to tell about the signal that is produced by the Chinese DCF77 receiver I used. This has a digital output and a 0 bit. For instance, this module produces a negative going signal. So a 0 bit is a negative low signal for 100 milliseconds, and a 1 bit is a low for 200 milliseconds. But the signal is too weak, so I put a MOSFET between it, but that inverts the signal. So the signal that is getting to the microcontroller is inverted. So for the microcontroller, this is the positive signal. A negative signal is coming out of the Chinese. Due to the FET converter, a positive signal is going to the input of the microcontroller. To not be confusing everyone, we do not talk about positive or negative. We are talking about active and inactive signal. It doesn't bother if an active is a 0 or 1, a high or a low voltage. So we just talk about active and inactive. To detect these incoming DCF77 signals, I'm using timer 2. It's a 16-bit timer, so it can count from 0 to 65535. The counter is running at a frequency of 230 Hertz. How do I know? Because normally the main frequency, the internal frequency of the internal oscillator is 16 megahertz. But I have some Chinese model. I have to study it more. In some applications it runs at 60 megahertz, but in my application I calculated it runs at a rate of 40.45 megahertz. Then I divide the signal by a factor through the prescaler of 512. That results in a frequency of 230 Hertz that is going into the counter timer, and that's our reference material where we check the times of the 0 bit, the 1 bit and the 1 second bit. Using this timer counter at a frequency of 28 kilohertz, 100 milliseconds corresponds to a counter value of 2823 counts. Of course, to double it to 200 milliseconds, 300 milliseconds, 400 milliseconds, and 1 minute, of course, 1 second, 28 to 30. This DCF77 application is using interrupts. An interrupt is an event that is occurring and it immediately calls a specific function that is connected to an event. An event can be a signal on some I/O pin of the microcontroller, or when a timer has timed out. So we use 3 interrupts. The first interrupt is on the I/O pin where the DCF77 signals gets into the microcontroller. In our case, this is port PA1. The second interrupt is the interrupt of timer 2, and it's called the compare interrupt. And the last interrupt is the timer 2 overflow interrupt. First, we will talk about the I/O pin interrupt. You can configure a port on the microcontroller, port A, B, C or D, to react on a high going edge, a low going edge, and a low going edge and staying low. Excuse me. So we only use the configuration where it reacts, generates an interrupt when the signal is going high, a high edge or a low edge. You can only configure a port. If I configure port A to be active on an active interrupt on a high going edge, then it means it's valid for all port A pins, port PA0 up to port PA7. But you can say especially that a single port pin, not a port but a port pin, can react. So I only enable port PA1 to be part of the interrupt party, and PA0 and all other ports won't do anything if something occurs on the input pin. Then we are going to talk about the timer 2 interrupts. Timer 2. The timer is set to a certain frequency. This means that it overflows at 2.3 seconds. The timer starts here with 0 counting up to 1 second, and then the value will be 28,230. Then it will count further on in the next second. It does not restart, it keeps up counting. So the next time its value will be the double value of it, 65 whatever thousand. But still below the maximum of the counter, 65. So this first it starts here at 0, counts up again, and then it comes to 2.3 seconds, which is the same as the maximum value, so it will overflow. If the counter reaches this value after 2.3 seconds, it will restart at 0. But normally it will never reach this value because some interrupts will restart the whole sequence. Why are we using this configuration? I mean, why should the timer count up to 2.3 seconds? First of all, when we talk about second in English, it means a part of the time, 1 second, but it also means the next one from the first, the second. So this is a little bit confusing where we are talking about. As the DCF77 transmitter transmits 59 bits each minute, and each minute has 60 seconds. So I am not talking about a second, 1, 2 or whatever, but I will talk about DCF time tick or DCF tick. And DCF ticks, I will enumerate them from 0 to 59, not from 1 to 60, but from 0 to 59. So after DCF tick 58, there should be DCF tick 59. But in DCF tick 59, the transmitter does not send out a 0 bit nor a 1 bit. It does not transmit any bit. And in the next DCF 0 tick, it will start again with sending out a 0 bit. Always a 0 bit at first. So there is a difference of 2 seconds between tick 58, tick 59 does nothing, and tick 0 restarts. So there is a 2 seconds gap, and we want to be able to detect this 2 seconds gap. That's why the timer is configured that way, that it can detect a 2 seconds time. The nearest configuration was to set the system clock 14 MHz, pre-scaler factor 512 division, then resulting timeout will be at 2.3 seconds. That was the nearest value, the most accurate value we can use. So now we are configuring our program to get starting to detect DCF ticks. First of all, we configure port A to react on an active interrupt, on an active going signal, and only port PA1 has to react on it. So we configure at this is a time moment, this is the timeline, this is the preparation time, preparation time. We configure port A and so on, and then we will wait here, and then suddenly the signal goes high. We are prepared for that. So an interrupt will occur at this moment, and this interrupt, we call it event 1. What should it do? Well, it should start the timer, which is not. I forgot something to tell. Before this whole process is going to start, first the application will wait for an active going signal, the first active going signal ever. Then it starts timer 2, and then it waits for the next active going signal, and then it checks timer 2 value. If it's more or less between 2000, between this value and this value, that's the tolerance, and the tolerance is set to, in the software, to 50%, which means 50% accounts to 468 counter ticks. So this is the ideal value, this is minus the counter ticks plus the counter ticks is if the received signal is between these two counter ticks, then it is accepted by the software as a valid 1 second signal, and each time this is detected, that's a valid value, then the timer will start from 0 again. So back to our interrupt system. Port A interrupts on an active signal. When this active signal occurs, immediately there is called another interrupt. It's called the interrupt handler. The same interrupt handler, but it knows if the signal was configured to act on an active or on an inactive. So this interrupt handler knows at this moment here that it's waiting for an active. So if it is detected that an active interrupt is awaiting, then it responds by swapping the interrupt in sensitivity. Interrupt sensitivity means not it seems an analog thing, but it's a digital thing. The sensitivity. Sensitivity means does it react on an upgoing or downgoing edge. So it swaps the interrupt sensitivity. It was waiting for an upgoing, and of course the next thing is there should be a downgoing here or a downgoing there. So set the interrupt to an inactive edge only, so it reacts. Clear, whatever, we will come to that later. And okay, this compare interrupt we will talk about now in between. First we will now talk about the timer 2 interrupt handling. The timer 2, as we said, to a prescaler value of 1502, so the counting frequency is 28,000. This means that if nothing is happening, the timer will up counting until its maximum of 65525, which is about 2.3 seconds. But of course, things happen before, normally. If a signal is received, then the timer will react on it by interrupt handlers. But first I have to tell something about the timer itself. It counts up from 0 to 65,000 if nothing happens, and then restarts recounting from 0. But there are two parameters that can be set. These are the array reload and these are the compare value. Letting timer 2 run, it runs just from 0 to 65,000 and then will restart at 0. Keep repeating it. But you can set when the timer is going to restart. Not at the end where it restarts automatically, but you can set the array reload value. For instance, if we set it to 1000, the timer will count from 0 to 1000 and then restart counting from 0 to 1000. So it will never reach the end. Another value you can assign to the timer is the compare value. The compare value should be lower than the reload value, otherwise it will not work. But the compare value is a certain value, say the reload value you set on 1000 and the compare value you set on 500. So each time the counter reaches the value 500, it is enabled to produce an interrupt. So you don't have to poll the timer counter value, is it 500 or more, so do something. No, you can enable an interrupt when the counter reaches the compare value, and then the software will jump to a compare interrupt handler. So we are using three kinds of interrupts. The I/O interrupt, which is used to detect a high going or a low going or another low going signal. And then we have the timer 2 compare interrupt, where we handle some things like to produce a beep, but also to control some other things. And then finally we have the overflow interrupt, when no signal is received within 2.3 seconds, there is something going wrong. So then the timer overflows and the overflow interrupt handler is doing some things. Again, we start with waiting for the first signal. The interrupt handler is prepared to act on an active going interrupt. Here is the active going interrupt occurring, and then immediately the interrupt handler is called, the interrupt handler of the I/O part, and the interrupt handler analyzes if it is configured to see an active going edge or an inactive going edge. So it knows what to do, and it swaps the interrupt sensitivity. So from going high, as I told earlier, from high, it now wants to detect a going low signal. Of course, that's natural. Depending in the interrupt handler, which is occurring here, in the interrupt which is occurring here, disable the I/O port interrupt, because if a 0 bit or a 0 bit or a 1 bit is received on both sides, well, then it has no use to try to detect another signal, because you know until 1 second has passed there will be no signal. If there is a signal, it can be distortion or whatever, the software doesn't react on it, it leaves it alone. So the I/O port interrupt handler is disabled for this time. But now the compare interrupt comes into view. If we start here at 0, then set the compare interrupt value to CC1. So at this moment, each time at the start of a second, the compare interrupt is set to this value, which is just when a 1 bit should be received within the tolerance of 15% is for the counter values. If it's just a little bit outside there or on the border, then the compare interrupt will generate a compare interrupt. Whenever, so the compare interrupt time moment is outside the 0 or 1 bit signal. So at this moment there should be received a 0 or a 1 bit, and the compare interrupt then checks also if a 0 or a 1 bit is received. If none of them is received, it reports a bit error receiving. The compare interrupt then will set the compare on a higher value to CC2. CC2 will set it to CC3, and CC3 interrupt will set it to CC4. We will skip the 2 and 3, we will explain later, so it's CC4. CC4 is the 1 second timing minus the offset, so it's almost near the 1 second moment, and then the software will re-enable the I/O compare interrupt, so it can detect active and inactive going signals. It's not stated here, but it will set it to active going signal. For now, the program is perfectly detecting a 0 bit or a 1 bit, but we also want to bring it out by a beep. The microcontroller, the STM8S103, has a beep peripheral. You don't have to create high-low going signals on an I/O port yourself. A peripheral inside the beeper peripheral does it for you. You only can set up the frequency with which it's producing a beep sound. But we want to have a stable beep. Each second, beep for a high, beep for a low. So we decided to make a short beep of 100 milliseconds, each time starting at this moment, stopping at that moment. Therefore we use the compare interrupt value from the timer. As I told you before, the CC1, it stops detecting I/O signals from outside. CC4, it restarts. But in between, if CC1 is occurring, it sets the value, the compare value, to CC2. There is set it to CC2. So in the same second, when this occurs, in electronics all things work very, very fast. Unbelievable for the human mind, but it does. So in 1 second, at this moment, it sets the compare value to CC2, and then an interrupt will occur, a compare interrupt will occur. And any interrupt compare, you always have to clear the flag, start the beeper. Depending on did you receive a low or a high bit, you have to store it. If you receive a 0 bit or 1 bit, you should use some global variable and you set in which bit you received, and then this will start the beeper on a high or low pitch. But also this event, because it checks the time, the exact time. I must tell you something very deep technical. Because of the clock frequency of the counter at 28 kilohertz, each step takes about 35 microseconds. So immediately when an interrupt occurs, the counter value is stored in a global accessible value. And then the interrupt handler is executed, which analyzes the counter value. Is it equal to the expected value? When using this timing considerations, when clocking at this one, so each clock takes 35 microseconds, but the interrupt handler, when it happens and stores the counter value, it only takes a few microseconds, only 2, 4, 5, 8 microseconds. It's very well within the 35 microseconds one step takes before the next steps occur. So the value you can check against can be the exact value you expect at that moment to be the counter value. Maybe a little bit confusing to you, but you can compare the exact value of the counter value you expect to be at that moment. Again, a little explanation about the counter values. When detecting a signal from outside, like the 0 and the 1 bit, you have to take into account some tolerance. But when you work with the internal compare interrupt, as I told you before, the counter counts up at a 35 microsecond speed. The interrupt handler checking or loading or reading the counter value takes only a few microseconds. So we need no toleration when using the compare interrupt handler. So finally, I hope you understand it a little bit more or less. If no signal is received, no 0, no 1, the timer will overflow after 2.3 seconds. It will call the overflow interrupt handler, and the overflow interrupt handler will reset the whole system, which is going to wait for a first active going signal, start the timer at 0, waiting for the next active going signal. Is it within the limits of 1 second, it will then start going on to interpret the 0 and the 1 bits, and if it's outside the expected range, it will resynchronize, restart, resync, meaning so waiting for an active going handler, starting the timer, waiting for the next active going handler, check if it is within the 1 second frame. If so, start interpreting the signals, or if not, just restart the whole resync procedure. Well, for so far this explanation of the software, and after this I will try to output the real time to some serial port to hyperterminal to make it visible. So I did a calculation. If I'm using a serial port baud rate of 115200, it takes about less than 1 millisecond to transmit 10 characters. So maybe I could use this compare interrupt to select some area here, but this is 100 milliseconds, and only a message to hyperterminal results in 10 milliseconds to transmit 10 characters, and I can create some place in second 0 to transmit data out to hyperterminal. But that will be some future goal to achieve. But for now, I hope you get a little bit insight in how a microcontroller can decode a DCF77 signal. Rest me to say thank you for watching this video, and I hope you learned from it. Bye bye.